at getting to the main question, which is about how do we learn a decision tree from training data. So let's get to that aspect today. So how do we learn a decision tree? So you're given some data now, which means you have certain feature values that have been recorded and the corresponding label has been recorded. So in our running example here, we have a bunch of people for whom we know what their refund status was last year, we know what their marital status is, and we know what their taxable income is, and we also know whether or not they cheated on their income tax returns, right? And now we are given a bunch of such people and information about them, and we want to be able to learn this tree that will do well at predicting the label, the cheat or no cheat for a new person, right? So how do we do it? And here's sort of the rough outline for all decision tree algorithms. So there are a bunch of them, like ID3, C4.5, CART, and there are more modifications that have been proposed in the literature. I'll give you a glimpse of some of these today. Essentially, they all sort of look something like this, and I guess this best describes C4.5. But yeah, I think almost all of them do something similar. So the way you start off by learning this tree is you pick one of the attributes which is going to be best in some way. We'll define what best means and how you pick it. But you pick the best attribute, and attribute and feature are really the same thing. So don't be confused when I say attribute instead of feature. It's just one is more common in literature on decision trees. So we pick one of the features or attributes for our current node. So when you're starting out at the top, it means we get to pick one of the three features, refund, marital status, or taxable income, as the variable associated with the topmost node. Okay, according to some definition of best that we'll get to. So we assign that to that node, and for each value that that feature can take, so if suppose refund was selected, it can take two values, yes or no. And first I'm describing it for discrete features. We'll also talk about how you do it for continuous features in a bit. But for discrete features, you just make a branch off of that node for each of the values that feature can take. So in this case, refund can take two values, yes and no, so we make two branches. So which is what this is. For each value of x, we create a new descendant of the node. And then we sort our training examples. So now we have a list of people which, for whom we are given all of this information, what their feature values are and their labels are. We take all of them, and just using the first variable, which is refund, we sort them into one of the two leaves. Okay, so you have all of this training data simply based off of one feature you chose, which was best. In some way, you split the training examples into, you sort them sort of down to the current leaves, which are just this and this, these two leaves, right? And if the training examples are perfectly classified, in the sense that everybody who had a refund of yes actually did not cheat, the label cheat for them was yes or no, as long as it's a pure label, you stop right there, you're done. But if you still get mixed labels, if you sort it by, for example, no, and you get people that were cheats as well as not cheats, you continue digging down further. Does that make sense? So you're taking all of your training examples, splitting just based off the first feature you choose, and see if you get all the labels. Everybody that's sorted to one leaf currently has the same label or not. If they do, you don't split further down on that leaf. If they are still mixed at this stage, now you go back and you repeat this process. You choose the next best decision feature or attribute, and you repeat this process. Okay? So I hope that makes sense. And you keep on doing this until either all of your training examples are perfectly classified, or you sort of reach the end, and in the sense that so we'll talk about specific stopping criteria and how you do the pruning. But then you basically go, once you have built your tree all the way down so that you have classified all of your training examples correctly, which can actually always happen as long as you're allowed to reuse your attributes, right? Ultimately, there are only finitely many training data, and their attributes take only so many values, and as long as you have explored all of them, you're going to be in a stage where once you have gone deep, you have built a tree deep enough, you will be able to exactly classify these points. But that, of course, seems like you are overfitting, right? Because now you're saying you can perfectly classify each training example. And we already know if you can do that, you're most likely overfitting. So then we go back and prune the tree in some way to reduce overfitting. And once you have arrived at the pruned tree, your decision for a new test point is just the majority vote of the labels of training examples that were assigned to that leaf. Does that make sense? So I know we have not specified several things here, but this is the overall structure of different decision tree algorithms. That you pick different features to split on, and you keep sorting down your training examples down this tree, and whatever are your current leaves, you just assign the majority vote of those training examples in that leaf to be the predicted label of any new test example that gets sorted to the same leaf. All right? Okay, so let's look at a specific algorithm, and then some of these things will be more concrete. So let's talk about ID3, which is the simplest one. So it does exactly this. It deals with discrete features. So we are exactly in this setting. So all the steps are the same. The only part is you keep sorting down your training examples, and earlier we said if the training examples classify perfectly, then you stop, otherwise you keep iterating, right? So one way that the ID3 implements pruning in some way is to say you cannot, if you have used a feature before, you cannot reuse it. Okay? So if I have split on refund here, I cannot reuse refund, say over here, even if the labels are still mixed. All right? So essentially it's saying you're limiting the depth of your tree. Your depth of the tree can be no more than number of features, right? Yeah. So this is one way it prevents overfitting, by saying you cannot build very, very deep trees because you're limited in how many times you can use one attribute. All right? So yeah, you just remove the current attribute and then you repeat this process. And when all the attributes are exhausted, you are done and you assign majority vote. This is only one of the ways to prune a tree. We'll be talking about other ways as well, that other implementations of the decision tree like C4.5 or CART implement. So is the overall structure okay? People fine with that? Okay. All right. So one key issue that we have still not defined is this notion of best. What do we mean by when we say pick the best attribute for each node, right? So let's get into that. So let's say here's a very simple example where we have two features and we have the corresponding label. So let's say this was your training data, if you will. And we have to decide, should we split on x1 initially or x2? So intuitively, which one makes more sense? X1, right? And why is that? You sort of believe that it matches y more than x2, right? And that is true. So the way we think about this is if we split on x1, the values true and false, and we look at the training examples that will get sorted to these two different leaves, we see that there are 4 trues here and 0 false for y, and 1 true and 3 false. So they're quite close to being perfectly classified. Whereas if we split on x2, we would get something like 3 true y's and 1 false y, and here 2 and 2 each. So it's a very impure split, right? So really, this is the notion we'll capture on to say which feature is best. Right? So we'll choose the feature, whichever features makes us more sure or increases our certainty about what the label should be. All right? Here we are not so sure compared to in this setting. Right? Yep. So of course, as you can see, uniform distributions of the labels is bad. If you did split on a feature and you ended up with your labels being still equally, the positives and negatives being equally mixed in each leaf, then that's not a good feature clearly. Right? So we can capture this idea of how pure a split is by looking at one notion actually of entropy that we'll get to in a minute. I wanted to put in another example because in the first one, it was very clear by inspection which one was the best feature, right? But the reason we need a criteria is because it may not be always as clear. So here's another example where you have, say you are at this node, it could be the starting node, and you have 29 positives and 35 negatives. And you can split on x1 or x2, and it gives you, that's the corresponding distribution of training labels in each leaf. And now it's not very obvious. You can't just say which one is better than the other, right? So we need a measure of how pure or impure a split is, right? Okay. So here's the way we'll measure how pure or impure a split is. We are going to pick the attribute or feature which yields the maximum, what we'll call information gain. So this is the criteria that ID3, C4.5, these algorithms for learning decision trees are based on, this notion of information gain, which basically measures the mutual information between your output label y and the feature xi. And you pick the feature that has the maximum mutual information between xi and y. Okay? And we'll talk about more more insights into what this means. But essentially, the mutual information between two random variables is equal to the entropy of one random variable minus the conditional entropy of that random variable given the other one. Okay, so we'll talk about what entropy means in a bit. But essentially, what this is saying is y has certain randomness associated with it. If I observed xi, now what's the new randomness? And if you look at the difference, whichever value of or whichever feature xi gives you a larger reduction in the uncertainty or randomness of y, that's the one we are going to pick. Okay? So entropy is going to be a measure of how uncertain or random a feature is. All right? So let's look at entropy a little bit more, but then we'll connect it back to this information gain. So here's the formal definition of entropy of a random variable. So if y is a random variable, its entropy is given by this expression, which is just the sum over all possible values it can take, the probability that the random variable takes that value times log of that probability. And more uncertainty implies more entropy. And you can see that here's a plot of the entropy versus the parameter p in a Bernoulli distribution. So for the Bernoulli distribution, you can look at what the entropy looks like for different values of p, and it looks like this. And this should make a lot of sense because when p is 0 or 1, what's your Bernoulli random variable? It's really deterministic, right? It's always either 0 or 1, or the probability of it being 0 or 1 is 1, right? So in this case, you're very sure of what your random variable is. So it has low entropy, right? So the more certain we are, the less entropy you should have, or more uncertain we are, which happens at p equal to half. Now each value is equally likely to occur, the more entropy we have. So entropy is, as you can see from this example, a measure of how much randomness or uncertainty is there in a random variable. Does that make sense to everyone? Okay, so even if you have not seen entropy before, which hopefully you should have, but having this picture in mind kind of helps. Yeah, so we talked about this. When p is half, it's like a uniform distribution over the values that the label can take, right? Both values are equally likely, and so we have max entropy. And when it's almost deterministic, then it has 0 entropy. And if you care about it, there's actually an information theoretic interpretation of the entropy. It is, again, for those of you who want to know it, it's the expected number of bits needed to encode a random draw from this distribution. So it's exactly counting how many bits are needed if I want to compress a random draw from this distribution. Okay, and this, you can read up much more about it. We won't go into the information theoretic interpretation, but just getting the idea that entropy relates to uncertainty is important. And here's how Andrew Moore explains it. So if the math does not make sense to you, I sort of like the slide that he used. So Andrew Moore is our dean of SCS. He used to use this slide, his son within low entropy state, where the values of his soup are sampled from entirely within the bowl versus when they are sampled from all over the dining room. So you can see that this is clearly a high entropy state. All right, so hopefully this picture will remind you of what entropy means, how random you are. Okay, so higher entropy means more randomness. All right, so let's get back to information gain. So we said that we can measure what's the benefit of splitting on an attribute by looking at how much observing or conditioning on that attribute reduces the uncertainty about our label. Okay, so that is, what's the entropy of y before we do any split? That's just how random is our y, right? Just the labels positive and negative, and you can compute that entropy by this expression. And then we can look at what's the entropy of y, what's the uncertainty in our labels after we split based off of a particular feature xi, right? And that's given by entropy of y given xi, and the expression for this is over here. Notice that it's very similar. So the only thing you have to realize, and this is a mistake people often make when doing the conditional entropy calculations, is we can take our definition for entropy and write a definition for conditional entropy, but you have to condition on a particular value of xi, right? So if I say condition on xi being little x, then sure, you can replace all these probabilities by conditional probabilities, right? And you get the corresponding expression for the conditional entropy. But this is your conditioning on one specific value that a feature can take. For example, when it's true, what is the conditional entropy, right? But to get the overall conditional entropy, you have to take the one that's conditioning on particular values and multiply it with what's the probability that feature takes that value. Okay? So it's like the expectation over this. All right, so that's why I wanted to put up this expression, so that if I just showed you entropy, you might be just doing this step, this later part, and not You also have to essentially weight by the probability that you follow that branch, right? If your marital status was married, you would be following one branch, and if it was single or divorced, you would be following another one. So you have to account for the probability that you take that branch, essentially. Yes?
Should there be a minus in the first line?
There is a minus? Oh, should there be you're right. There should not be, right, because I've written the entropy. You're right. So yeah, that's a typo. This should be plus. And then the minus here comes from the definition. Thanks. Yeah. That is a typo. So yeah, make this negative a plus, the first one only. All right, so as we said, information gain is just this difference. Before I split based off of some attribute xi, and after I split off of it, how much is the information I gained by observing xi, right? And we are simply going to pick the one that maximizes the information gain. And as you can see, the maximum information gain criteria is really the same as the minimum conditional entropy one. We don't really need to compute the entropy of y unconditioned, right? Because we are optimizing over which attribute to pick. And this is independent of xi. So all we care about is picking the one that has the minimum conditional entropy, which should make sense. Given xi, now you have the least uncertainty about y. All right, so actually let's do this small calculation for this example we had and convince ourselves that indeed splitting on xi makes more, I mean, it made intuitive sense, but that it also makes mathematical sense according to the information gain criteria. Okay, so let's compute the entropy of y given x1. So let's go back and quickly remind ourselves. So we are only computing this. We don't need to compute the entropy of y. So all we have to do is we are going to consider all the values it takes. In our case, the x1 and x2 are only going to take true and false, only two values. We are going to look at the probability. We are going to plug in the estimate, right, that it takes true value or false value, and then look at this conditional entropy. So that's what we have here. We have half is the probability that x1 is true, because it happens in half of our samples, right? Half for when it takes value false. And then we are doing the p log p kind of argument, right? So then we have that it's when x1 is true, y is always true, right? So the probability, again going back, so the probability that y is true given that x1 is true is 1. So we have 1 log 1 plus 0 log 0 when we condition on x1 being true. And we have, as you can say, when we condition on x1 being false, we have 1/4 of the times y is 1. So we have 1/4 log 1/4 and 3/4 log 3/4. Right? So I hope people follow that. We can write the same. So instead of simplifying this, first let's write the expression for the other case, which is the entropy of y given x2. Again, x2 takes the value true or false half the time. So the weight up front is half. And then the p log p terms are now, whenever it's true, we see that 3 of the times y is true. So we get 3/4 log 3/4 and 1/4 log 1/4. And when it's for the other setting, when x2 is false, we see that half the times it's true, half the times y is false. So we get half log 2 and half log 2, log half, sorry, half log half and half log half. All right, now you can actually directly compare the expressions. You don't even need to simplify them. You can see that, first of all, this term goes away because log of 1 is 0, right? This term, you can verify, is actually bigger than 0. And the other two are actually this. Oh, I didn't cancel it, but like these two terms are the same. So you don't need to worry about them. All you have to do is compare this and this. You see that this is 0 because log of 1 is 0. And this term is 0. And this is something bigger than 0. So you have that the entropy of y given x2 is larger than the entropy of y given x1. Means that observing x1 reduces your uncertainty more than observing x2 for y. So it agrees with intuition. Right? Any questions on this? Everybody okay with what we did here? Yes?
Are we just assuming all the attributes are independent to each other?
All the attributes are independent. We are just conditioning on them, right? I don't think this necessarily assumes independence.
So it doesn't matter when you construct a decision tree, we can choose the attributes no matter.
Right. So information gain criteria at least says you're going to pick one at a time, and you just pick whichever one gives you the most decrease in entropy, right? They could be, yeah, they could be dependent. Yeah.
Can you give some more intuition on why we multiply by log?
Oh, why we multiply by log? So this is just in the definition of entropy, right? Yeah. That's actually the number of, again, if you go to the information theoretic interpretation, that's the number of bits needed to encode something. So if you have, I don't know if there's an easy way to say it. I guess if you have a random, yeah, I don't.
So maybe one way of thinking about it is, suppose that you roll, I don't know, a 16-sided die, right? An even probability of having any one of the outcomes. Then you have 16 outcomes, you need 4 bits, log 2 of 16 to encode them. But if the die is weighted and some outcomes are more likely than others, you need less than 16 bits on average to encode them. For example, if half the time you get 1, then you can assign just a 1-bit string to encode 1, and then you use slightly longer strings to encode the less likely choices. Right? Huffman coding is a particular algorithm for assigning the bit strings.
Yeah, actually a simpler, yeah, so that's a great example. A simpler one I was going to mention is just coin flips. That's the Bernoulli one I mentioned earlier, right? And you can see it from there that if P is half, when both your heads and tails are equally likely, you exactly get that you're using 1 bit of information.
Right.
Right?
Right. The reason I didn't use the
but that's more
informative
informative.
is that you have to use fractional bits.
Yes, yes.
So it's a lot
Which
more complicated argument.
Exactly, right. Yeah, yeah. Because then you get fractional bits, yeah. If the probably P is not half, right?
Right.
Yeah. Okay, so hopefully that gives some intuition to you. Yeah. All right, any other questions? Okay. All right, so yeah, we talked about this. So here it's so which feature is the best to split? We can at least so far we've been talking about the discrete feature setting. At least there, all you have to do is compute this. We pick the feature which maximizes the mutual information, but that's equivalent to just picking the feature which minimizes conditional entropy, and that's all you need to calculate, right? What about continuous features? So we do something similar. What you do essentially is you take your continuous feature and you want to split it along some value, some threshold, to essentially convert it into a discrete variable, right? Is your feature bigger than 2.5 or less than 2.5 as an example? But how do you choose 2.5 and why 2.5 not some other value, right? So there are infinitely many possible thresholds you can sort of choose. You're still going to use information gain, but how do you pick this right threshold? And the idea is you can evaluate the information gain for different thresholds and pick the one that gives you the best result. But you don't need to search over infinitely many. And the reason being that you have a finite amount of training data, right? So if you only have n training points, then the corresponding feature, say you look at x1, that feature can only take n possible different values, right? So you really only need to search over essentially n or n minus 1 if you want to be exact, different thresholds, right? So for one training point, my value was, the smallest value I observed, say, was 0.1. The next unique value that occurred was 0.3. So I only need to test in between. I can put a threshold at 0.2. So between any 2 consecutive values that you observe, you only need to test for those thresholds. So you only have essentially n minus 1 candidates, thresholds to check. So you have to do the information gain calculation not only for every feature, but for different values of that feature. But for each feature, you only need to use no more than n values or thresholds. Is that clear? So that's how you would handle continuous features. All right. So you can talk about, well, how expressive are decision trees. And this is sort of clear. We talked about it before, that in general, if you don't prune them, if you just keep building them, you can literally handle any expression, right? You can learn any function of your input features, particularly in the discrete case, right? You can imagine having a truth table, and you can represent any truth table by a decision tree that's deep enough, right? You can always get down to, you can essentially literally take every training example and have every training example be associated with one path in the tree from the root to the leaf, and exactly the label of that training example in the leaf node. So you can perfectly classify all training examples, and that's why pruning is actually important, right? So you can keep on doing this information gradient criteria and learning your tree deeper and deeper if you don't limit how many times you can use an attribute, but then we need to avoid overfitting by doing some pruning. Okay? So it won't generalize well, and so in practice you want to prefer compact decision trees. And we have seen how ID3 does it by limiting you to use one feature only once. Why we might want to do it, again, this is just looking at that bias variance trade-off again. So we can have, say this is your ideal classifier, we can have a decision tree based off of this partition. So every partition you should be able to map it to a tree, right? Essentially we are splitting, at least in this example, we are just splitting each feature along half or 1/4 and so on, right? So this is x1, this is x2. I'm splitting x1 along its mid-range, x2 along its mid-range, and then just repeating that process many times. So we can have a coarse partition or we can have a fine partition, more leaves versus less leaves. You can imagine a tree built on each one of those. And you can see that if I think of what's the best fit I can get by assigning one label to the leaf here, then this is maybe the best fit you can get using this partition or this tree to the ideal classifier. Whereas using this partition, that's the best approximation you can hope to get, right? So here I'm really talking about bias. So you can see that this coarser partitions or shallower trees are biased, right? And the deeper ones have smaller bias. But if you look at variance, if I relearn this tree on a different data set, you'll see that this one will not tend to vary much, whereas this one changes quite a bit between different data sets. So again, getting at this idea that you might, because you have smaller and smaller leaves, how many training data points you get in there will change much more, and you'll get an unstable estimate. So that's again going to the, by choosing the right depth or the right number of leaves in your tree, you can do the bias variance trade-off. So what are some other ways of actually doing this pruning, apart from the one that ID3 uses? So some strategies are, which we talked about, is pre-pruning, which is what ID3 does. You just fix the depth to be equal to the number of attribute. You can also fix the number of leaves. And actually that might be more reasonable. There is at least some theory to support that number of leaves is the right complexity and not the depth when we are talking about how complex a decision tree is. We will revisit this issue when we talk about learning theory, VC dimension, and so on. That what's the right complexity, right measure of complexity of a decision tree. In all the other examples we have seen so far, it was very easy. K nearest neighbors, what controls the complexity? K, right? Yeah, number of nearest neighbors. In histograms, it's the bin width. In kernel regression, it's the bandwidth of the kernel, right? And so on. So it was quite easy. For decision trees, you can think of either the depth or the number of leaves. You can have a tree which has a lot of depth, but still have fewer leaves if it's very unbalanced, right? So we'll get to the question of which one is better.
If you're going to have a fixed number of leaves, though, then don't you need some way to decide which leaf to expand next among all your choices?
Right. So then once you fix the number of leaves, then you follow some other rules to decide which ones to keep. So let me get to the other points also. So I just wanted to mention these as sometimes, and actually that's the way CART does it, you actually use the number of leaves as a penalty. So you have a likelihood term, and you have a penalty term, which is the number of leaves in your tree. And then you use some kind of dynamic programming to optimize that regularized objective. That's one way to do it. But otherwise people use, and actually this is what C 4.5 does, it uses some tests to decide which rules to keep. And that's more like post-pruning. So you might have decided how many leaves you will keep. Every leaf you keep is associated with one decision rule, okay, that goes from the root to that leaf. Okay, so you can, let me mention what this does, and then it'll make sense. So what you do is you convert your decision tree into a set of rules. If marital status is this, taxable income is this, and whatever family income is this, you are a cheat or not a cheat. So these, you can list out all these. By following a path from the root to every leaf, you can write out a set of decision rules. You do that, so you convert your decision tree into a set of rules. And so here would be one rule just following this to this leaf. And after we have written out all of these, you eliminate variables which are independent of the label. Then you use some tests, and we won't go into details of which particular tests. C 4.5 uses the chi-square test for independence, but you check which of the variables values in your rules, so marital status being equal to married, is that actually independent of the label? And if it is, you remove all such rules from your list. Okay, so that's one way to do it. And then you simplify your rule set by eliminating rules in which your label is independent of the value assigned to one of your variables in that rule. And you eliminate all of them. That's one way to do it.
So how do you put the tree back together at the end? Do you put the tree back together again?
So you put the tree back together, and again, there are different ways. You either use an OR rule or an AND rule, essentially. So if you have eliminated one variable, you can eliminate all the rules in which that variable was involved, or with that particular value was involved. That's equivalent to pruning that particular branch of the tree. Yeah.
But typically, like often you would wind up using the rules just as a set of rules
you could,
and not
you're right.
putting them back together, right? That's one of the advantages of turning it into rules before pruning.
Sure, yeah.
Gives you more flexibility.
Right, exactly. So that, yeah, it's used both ways. People do prune it back or not. You can just use the set of rules to output your, but then you have to store, which I guess you have to do anyways. You have to store the decision tree or the list of roots, right? Yeah. All right, so this is what, so I guess you've sort of at least seen two flavors, ID3 which fixes depth, C4.5 which uses this kind of, writes it as a set of rules and eliminates rules by testing whether variables are independent of the label or not. And cart, which I briefly mentioned, I'll get to it in a minute again, which uses some penalty based off of number of leaves. Right? Actually, yeah, that's the next one I'll get to. So there's also something called information criteria, or the minimum description length, that's used to prune trees. And essentially the idea there is that you have a term, whatever loss you're optimizing. So the loss could be least squares loss if you are doing regression, or it could be the 0-1 loss for classification. So you have your favorite log loss rather over here, and you add a penalty which depends for each tree, which could be just proportional to the number of leaves. And cart actually does that, and it optimizes this joint objective. And again, we won't go into this class. If you want to read on cart, there is a dynamic programming way to optimize this penalized objective. And there are several actually modifications people have. So people have played with, is number of leaves the right thing, or is the volume of the leaves the right thing, or maybe the square root of the number of leaves is the right thing. So there are lots of things people have shown about what's the optimal penalty to use here. So there's a lot of work on that, but we won't go into those specifics. So at least at the minimum, I think you should know about ID3, which is the simplest one, and then have some idea about these other approaches to pruning. Okay, so any questions on this? This is using decision trees essentially for classification, right? So you have seen what they represent, how given a decision tree you can output the label of a test point, and now we have seen how you can learn a decision tree given training data, which completes the story. What about regression? So essentially what we did in classification was you learn a tree, and then at the leaves you assign the majority vote, essentially, right? What about regression? What would you do? Something quite similar, right? Except that once you have sorted your examples down to the leaves, your labels should be, yeah, like say the average, for example, right? Or in fact, you can do any kind of fit using the training data that have been sorted to a leaf. So instead of just majority vote, just like we did for in the kernel regression setting, or histograms also we talked about, all you do is you either do average, which will be equivalent to a constant fit. You can do linear fits, you can fit polynomials, you can make it very, very fancy, right? So once you have learned learning the tree structure is really the main thing, and after that, it's quite similar in terms of what you do. So here's one example of regression trees. So here the data is, say, now instead of predicting whether a person cheated or not, you are trying to predict their age based off of things like their gender, are they rich or not, or number of children, and how many times they travel per year, and so on. And here's a tree you could possibly learn. So you split on number of children being bigger than or less than 2, gender, and essentially, yeah, the predicted ages. Once you have sorted down all your training examples, you still pick these features based off of information gain, right? And where to split also based off of information gain. Once you have learned that tree and sorted down all your training examples down to the leaves, then you just do an average in this case to predict the age. But as I said, you can get fancier and do whatever kind of fits. Makes sense.
In that case, the outcome of a regression tree will become only a limited number of discrete real values.
any values of a real number?
It's as many as number of leaves in your tree, right?
Yeah.
Yeah, so you are, that's exactly the same as, say, you were using histograms or something like that. Once you fix the number of bins, you only have that many unique values. But the number of bins can increase with number of samples. And here also, typically, the depth of the tree that you learn, or the number of leaves, tends to increase with number of training data.
But given a limited number of training data, you only have a limited
Yes.
number of outcomes.
Yeah.
What was different from the other regression methods?
Sure, okay, right. In that sense, yes. Yes.
Can I add something?
Yeah.
You can have any sort of regressor at the end. Like
Yeah.
all that you've done is done some sort of, in some sense, like pre-splitting your data in different cases.
Yeah.
Your tree saying, if you're under this sequence of rules, then you've got this sub-data set, and you can do any sort of regression there. The example here is the basic regression of take the mean. But you could do a general regressor out there for just a subset of the data. So it's just a way of like building kind of like hierarchical model where you first do a split of the data and then you regress.
Yeah, actually, that's a good point. Like, that's how, at least I started out by motivating this, that you should just think of it as we are now going local in terms of the fits we are doing. So once we have localized our data to each leaf, right, which corresponds to a certain range of values of each features, you can do whatever. You can fit polynomials there. You can fit, do all the fancy, any regression method that we have talked about so far within those leaves. Right? And in that case, yeah, it won't be, have that, yeah, thanks, Ada. That's a good point. Yes.
Then what? So if let's say you want to fit the linear fit, right? So what is the x and what is the y? So let's say this problem, instead of having.
Well, the goal then is that you don't believe a linear model, a global linear model is not a good fit for your data. What you are trying to do is do piecewise linear fits on your data. Does that make sense?
I just wonder, like, in this example, we say predicted age is 35.
Right.
So you take the mean of
all the data. So you look at this list of data for which you actually know the age. I'm going to sort it down. So every example in my training label for which the number of children is bigger than 2 and the gender is female, I'm going to take that sub-collection of my training data and I'm just going to average their ages. And that's the prediction here. Does that make sense? Right.
But what if you want to do a linear fit on that subset? Like
Yeah.
What is the independent variable and what is the dependent variable?
You can still use all the features as your x's, as your features and the labels. It's just that now you've restricted yourself to a smaller set of data. Right? So you look at all training examples for which number of children is bigger than 2, gender is female, but then you look at all the attributes of those and you just do a linear fit as you would with this subset of the data. So as Ada said, it's just a way to literally divide up your data into smaller subsets.
So one conceptual thing is that once you split, some of the attributes might be constant in that subset,
right.
And then you can just throw them away. Or if you're doing ridge regression, their weight will go to 0 anyway.
Yeah. Right. Yeah. So not all of them will be relevant once you have done your data split. Right? Does that make sense? Other questions? Okay, so let's wrap up the part about decision and regression trees. So what we have seen is, and actually they have been very popular for many years until recently when we have started talking about high dimensional settings, because then it becomes a little tricky to build trees, or at least they can become exponential in the dimension on how quickly you learn them, unless you enforce things like only use one attribute once or things like that. So getting them, pruning them in the right way becomes trickier the more features or attributes you have. But still they are used quite a lot, at least when you have low dimensions, because they are very simple. They are interpretable. So as Jeff was just saying, once you have your leaves, you sort of have a sense for which features define this subset of my data. So it's very, very interpretable in terms of what features are relevant at predicting something or not. At least you can look at the leaves and they give you some information about that, right? So they are very interpretable. It's sort of easy to implement provided number of features is not too large. And yeah, you get good performance. We talked about information gain as the main way to select which feature to split on. At least that's true for IE3 and C4.5. CART has a slightly different approach. where you are optimizing this regularized objective. And in general, yeah, you should know that they will overfit unless you do some kind of pruning, which could be a pre-pruning, post-pruning, or this complexity penalized approach we talked about. And we talked about them for classification and briefly for regression, but you can use them for anything. You can even do decision tree, or so you can even do decision trees for density estimation. Right? So you can sort down your training examples and then come up with some estimate for your density in each. Just like you were doing it in each bin, now you would do it in each leaf, relative counts, or something like that. Right? Okay. I think that's all I had for decision trees, and the plan is to continue with something which builds, which builds off of decision trees next, which is boosting. So, did I get it? Okay. Are people up for it? Do you want a little break? I know we're doing a slightly different topic. We can take 5 minutes break if that helps. Sure. All right, so let's talk about boosting, which has a nice subtitle called "Can we make dumb learners smart?" Okay, so the idea here is that it's sometimes very easy to come up with learning rules that are very, very simple, maybe too simple to be useful in practice, but can we take a bunch of such very simple rules and somehow combine them and get something more intelligent, right? So first of all, why would we want to do that? Here's an example where you want to categorize the type of call that's been requested. So somebody picks up the phone and either wants to make a collect call or wants to pay by using some calling card or whatever type of call it is. You want to categorize that. And so you see text or actually speech, something like this, which says, yes, I'd like to place a collect call long distance. And you want to take this sentence and be able to classify whether the person wants to do a collect call or charge it somewhere and so on. Now it's very easy to say, well, whenever the word card appears, like if somebody says card, then most likely they want to either do a calling card or put it on some credit card or something like that, right? So you can come up with these rules that are not accurate. They don't directly get you the label. For example, you can only say it's calling card or credit card, but it's a simple rule. If card appears, you do something, right? So something like that. So it's very easy to find rules of thumb that are often correct, but they are not very accurate, right? So it's hard to find one single highly accurate rule. So can we take many such rules? So I can say maybe if it has card, maybe if it says billet, like if it says billet somewhere, right? Then we know it's a third party kind of call or something like that. So you can come up with these simple rules that by themselves, no one rule will be sufficient, but maybe there's a way to combine them to get at more efficient rules. So that's the idea behind boosting. And it's essentially about, again, getting back to this question of finding the bias-variance trade-off, which is what we did with decision trees. And the idea is sort of this, that weak learners, so we'll call these weak learners simple rules of thumb. These weak learners, they have low variance, right? For example, just a line, or maybe if you think about decision trees with just one split along each feature allowed, they are very, very simple rules. They don't usually overfit, but they tend to have high bias, right? So can we somehow combine many of them together to improve on their bias while still using the fact that each of them has low variance, somehow do a better bias-variance trade-off? Maybe we don't have to combine too many of them so that we can increase our or reduce our bias, but not increase our variance too much, hopefully, right? So that's sort of the idea. Can we make these learners always good? Of course, when I say always, the answer is no, but often yes, right? So when can we do this? So actually, there are many ways to do it. What boosting goes after is, well, we are going to learn a bunch of such weak classifiers, and you can just combine them by averaging or something like that. Actually, that's also done, and it's known as bagging, which we may or may not get into. But what boosting says is, what makes sense is that we'll have many such weak learners, but we'll assign each of them different tasks. We'll want each of them to be good at a different part of the input space. So some of them will be more sure about certain regions, saying what the label is. Others will be more sure about other regions. And now we can form combinations of them. Like a very simple example here is this, say, for example, decision stump. So a decision stump is when you have a decision tree, but only of depth 1, essentially. So we'll be referring, that's often a weak learner used in boosting. So that's why I think it just kind of follows naturally that often what we are boosting is decision stumps, which are one-depth decision trees. Okay, so you can have something like this, which splits one part of the space. It knows that the label here is +1, -1. Here it's not as sure. And maybe there's another one which is reverse. And we can just combine the two of them by summing them. Or more generally, you can form some weighted combination of them and use its sign as your final classifier. Right? But the key is that we want, so these h sub t's are going to be different weak learners. And we are going to want them to be more confident about certain regions of the space than others. All right? So classifiers that are going to be more sure, so the weight is going to depend on how sure a classifier is of its output. So they are, the ones that are more sure will have a larger weight, and they are going to sort of, you can think of this as doing a vote over all your classifiers, and they're going to vote with more conviction. And also the classifiers are going to be more sure about certain parts of the space than other parts. Okay? All right, so hope is on average they'll do better than a single classifier. So the key is, how do you get these classifiers, how do you learn these weak classifiers to be more confident about certain regions of the space than others, and then how do we set the weights of each of these classifiers, each of these weak classifiers. Okay, so first of all, I hope everybody is comfortable with what, when we say weak classifiers, what do we have in mind? Some very simple classifier. For example, a linear classifier, for example, decision stumps of depth 1, or for example, maybe nearest neighbors, but with a very large value of k. Those are usually not used. I think the most common ones that are used are actually decision stumps that are used in boosting. But you can think of some very base kind of classifier that's simple and has large bias. Right? So we are going to assign them different votes, and how do we make them learn about different parts of the space? So there's a very simple trick you can use to learn weak classifiers that are more sure about certain parts. And the idea is as follows. Let's take our training data and let's reweight the data. So I can say that my training data is not the original training data. I'm going to make some of them have, one extreme is I can just remove some of them and only leave ones that are in certain region of the space, and then ask a classifier to only learn on that subset. Or not so extreme cases where we weight our training data points differently. So we'll assign a weight to each data point, and we are just going to learn a weak learner every time changing the weights on our training data. Okay, so let's get into this idea a little bit more. So that this is really what boosting is. That on each iteration, we are going to weight each training example by how incorrectly it was classified by the previous weak learner. So we learn a weak learner, first maybe using equal weight on all the data points. It's going to be incorrect on some examples. We are going to increase the weight of those examples, decrease the weight of the ones that were correctly classified, and then relearn a weak classifier. So a very simple idea, but it's really cool, works great both in practice and theory. So we are going to learn a weak hypothesis once we have assigned weights to the training examples by how incorrectly it was classified by the previous weak classifier. And then we learn a strength for this weak hypothesis. How much should it contribute to the final decision? If it's able to do pretty well, then we'll have it give it higher weight, otherwise we'll give it lower weight. And we'll see exactly how to set these weights in a minute. All right, and the final classifier is just going to be, we combine a bunch of them with different weights and output the sign of that linear combination. Does that make sense? At least the basic framework. Right, so as I said, practically useful and theoretically very interesting. So the question is, how do we, suppose we have decided what weights we are going to give. So there are two things here. Of course, we can pick, or three things rather. We can pick which class of weak hypothesis to use. For example, we'll say decision stumps. Then we need to decide what's the strength for each hypothesis and what's the weight we give to the training examples, right? But suppose we have fixed the weights. How do we actually learn a classifier on weighted data? What does it mean, right? Because so far we haven't done that. We have not talked about weights on the training data. So here's what it means. That consider you have di is the weight of the ith training example, right? Then one way to interpret it is that the ith training example is not one training example, but it sort of counts as di examples. It's as if you took that example and replicated it many times. Of course, your weights can be fractional, and then you're talking about having replicated it fractionally in some sense. But essentially, so that's one way you can think about it, as if you have many such instances. Or you can think about it that if you were to resample the data, you would get more instances of the data points that had heavier weights and lesser instances of the data points that have lower weight. All right, so that's at least intuitively how you can interpret weighted data. And how you learn on it is that in your calculation, so for example, you're doing maximum likelihood estimation, and the counts show up, right? So something like count of a variable taking a particular value shows up. When we are going to estimate these counts, we are just going to, so a count was how many times, so if we have m data points, we are counting how many times was the label equal to little y. Now we are just going to multiply it with the weight, right? Which is as if we are now counting, we replicated the ith label di times, and we are adding some extra counts for each of the labels based on what its weight was. So really, that's all the change you have to make as far as how to learn a weak classifier on weighted data. All right? Does that make sense? So it's a simple idea. You require slight thinking to make sure that how you learn a weak classifier on training data, it's as if you have some pseudo training data points that are proportional to the weight of that data point. Okay, that's the way to think about it. All right, so let's talk about a specific boosting algorithm called AdaBoost and how it gets these weights. Yeah.
Sorry, question. Yeah. It seems like what you're describing, you have your first weak learner, which basically picks the best of everything, right? And then now you
well, it's a weak learner, so it's not going to be very good at classifying your data points, but yeah,
but
right.
Then you have some new points that weren't classified very well, and so you learn new.
Actually, they're not new, so that's the,
Yeah, sorry,
you just reweight them.
Yeah, exactly.
Yeah,
so you have
yes.
some points that weren't classified by the first one, and then
Yes.
you run a second classifier or something like that. At test time, do you do something so that you try to figure out which of those classifiers?
No, so the test time, your final output, final classifier is just a weighted sum of all of these. Right? So you just classify according to this.
Because at test time, you don't know how well each one's doing because you don't have the label until after you make a prediction.
Right. I guess I was just wondering if there's anything where like, or if there's any extension to this where you try to figure out like a region that it belongs to.
Yeah, it's often called a classifier cascade. So the idea is you do like a cheap classifier to winnow out a lot of examples of one class, and then a slightly more expensive classifier to rule out most of the remaining examples of that same class, right? Like you're picking off things that are mostly uniform, mostly pure, and like classifying them and saving your effort for the places that are hard, where the decision boundary is doing something complicated.
Right. So there are many variations, and actually we'll see an example of this in a minute that will pictorially help you maybe relate these things a little bit more. But before we do that, I actually wanted to present the algorithm and say one specific, so there are many flavors of boosting algorithms. We'll look at one of them and how that one updates the weights. And this is the most popular one. It's called AdaBoost. And what it does is as follows. So here you have your training data, m of them. And again, the labels, let's say, are plus and minus 1. This is without loss of generality. They could be 0 or 1, or we'll talk about it at least for binary classification. But having it minus 1 and plus 1 helps, as you'll see. We initialize all the weights. So D1 is the initial weights for the ith training example. So it's the same for all of the training examples initially. If you have m data points, you give 1 by m weight to all their data points, just equally. And then we are going to iterate over many iterations, and we are going to train a weak learner using the current distribution, which is going to be dt. And we just talked about how to do that, right? And we'll get a, right, so I talked about initially equal weights. So this could be something like naive Bayes or decision stumps here. We'll get a weak classifier, and then we are going to choose a weight for that classifier based off of basically how well it's doing. So I'll get to the choice of the weights in a minute. For now, think it's a magic positive number, which tells you how good HT is on the current weighted training data. And then we are going to update the weights on the data points as follows. If the weak classifier HT gets the label correct, we are going to decrease the weight by a factor of e to the minus alpha t. And if it's incorrect, we are going to increase its weight by e to the alpha t. And this zt is just a normalizing factor that makes sure your weights sum to 1. Okay? So you can essentially ignore zt initially, and just say I'm updating my weights, either increasing them or decreasing them based off of whether I got the label correct or not. And ZT is introduced to make sure all the weights, the DT are t plus 1 sum to 1. Okay. All right. So yeah, and you can see that I can go from this expression to this expression just by introducing yi times ht of xi, right? Because this product is going to be negative if you got the weight wrong, and its product is going to be positive if you got the label right. So it automatically gives you e to the minus alpha t or e to the alpha t. And this tells you why choosing plus or minus 1 helps, because then you can think of these two cases, whether you got the label right or not, as one expression. All right? Okay, so that's good. And then, yeah, I said this is just a normalizing factor, making sure you sum to 1. And here's your final classifier. It's just the sign of a linear combination of your weighted classifiers weighted by this weight alpha t for each classifier. So there are two sets of weights here that you have to be careful about. One is the weight on the data points, and another is the weight on each classifier. So weight on the data points, this is how you update them, that's dt. The weight on the classifier is alpha t, that I'll tell you in a minute how to set. All right. Okay, so in fact, let's talk about what is a good setting for alpha t. And what's recommended in this original paper that talked about boosting is that we should set it to be half the natural log of 1 minus epsilon t over epsilon t, where epsilon t is essentially the probability of or probability of error for the classifier ht on the current weighted data set dt. Okay? So how do we calculate the weighted error? That's just saying we are counting whether or not you got the label right and then multiplying it by the weight of the training data point. Okay? So that's your weighted training error, and we just plug that weighted training error here and get a weight for the corresponding classifier. So we are taking how good this classifier did on the current set of weighted training data, and then we can change the weights of the next iteration. So why does this rule make sense? Well, if your weighted training error was 0, it means that HT is perfectly classifying all of the weighted data points. It might still be doing wrong in terms of the original data points, but we are talking about the error on the weighted data points, right? So alpha t is, in this case, if I plug in epsilon t equal to 0 here, you see that alpha t is infinity, right? Which makes sense because this is a very good classifier. For the current set of weighted data points, it's able to predict perfectly well. I give it a lot of weight. If epsilon t is 1, then it gets all of them wrong. And if I plug in epsilon t equal to 1 here, you will see I'm doing log of 0, right, which is minus infinity. So I'm giving it minus infinity weight, which makes sense again because it's perfectly wrong, which means the negative of that is perfectly right. Yeah, so if I give it minus infinity weight, it's contributing the same to my overall linear combination. But if it is a useless classifier, it's completely outputting randomly 0 or 1, then epsilon t is 0.5. It has half weighted training error, and if I plug in that here, we get a 0. Alpha t is 0 because it's log of 1. Right? So it makes intuitive sense. Okay, any questions on this? Maybe let's see an example. Oops, that's reminding me to end up in 10 minutes. But let's see an example, and then hopefully all of this will be much more clear. So here is, let's say, a data set. This is the initial data set we'd start off with some positive labels, some negative labels, and the size of each plus or minus tells you the weight. So initially they're all drawn of the same size, so they have equal weight. So let's say we learn a decision stump, just a single split along a single feature, let's say. So what could be a decision stump we could learn on this? So just something that minimizes the number of mistakes. Any thoughts? I'm saying split one of the features, only one feature along some value. So I'm only allowing for essentially splits like this or this, vertical or horizontal splits only once through this data set.
If we pick x1 to be the feature, we can get a...
so yeah, maybe something like this,
yeah.
Right? Yeah, that would make sense because that's getting the two positive rights, all the negatives right, and making an error on 3 of the positive points, right? So this is in fact the first weak learner you will learn. and it has an error rate on the weighted training. So the weights are now equal. So you make a mistake on 3 out of 10. So you have epsilon 1 of 0.3, weighted training error of 0.3, right? And you use that epsilon, you plug it into this formula and get a corresponding alpha, right? So in this case, it turns out to be 0.42. All right, so now we are going to, these are the 3 ones we made a mistake on. We are going to increase their weight. We are going to reduce the weights of everything else. So we made these larger. The remaining ones we made smaller because we did well on them. And now we are going to relearn another single split along one of the dimensions that does well on this weighted data set. And what do you think that might be?
Including the 3 data points.
Yeah, so you will sort of want to get all of these right. So it turns out that if you do something like this, you are going to do pretty well. You can check actually, I think any other way of doing it will give you more errors, or maybe same. Yeah, I think it gives more errors. All right, so we have now a weak learner which goes like this. And it makes, again, 3 mistakes, these 3 ones. Of course, not all the data points have equal weights, so we have to do the weighted training error is no longer 0.3. You have to take the weights into account, right? And if you compute it, there's a certain value for it you get. And you can plug that in to get the corresponding weight of this classifier, which is 0.65. So at the next step, what we are going to do is we are going to, these ones, the ones that were right, these 2 positives and these 2 negatives, they were right on both the first and the second iteration, so they are going to shrink even further. These ones are going to be smaller than right now. These ones are going to be larger than right now. Right? So we get something like this. And we'll relearn another weak learner on this. Right? So we get something like that. Right? So now we are making a mistake on this, this, and this. But we are doing a good job on the ones that have large weight. And again, you can keep on doing this for many iterations. And your final output, sorry, the colors are not great here, but hopefully you can see those in the PDF, is the sign of each of these classifiers multiplied by the weights we calculated for them, the alphas. And you can do it, and for this case, the final decision boundary you get is something like this. So you can see that even though we started out with only axis-aligned splits, our final classifier has a more complex form. So we have actually reduced the bias. We're allowing for more complex decision boundaries, hopefully lower bias with this. And we have been able to take very weak learners and get something more complicated out of them.
So for the last one, the threshold is 0. The threshold for the overall
Oh, there?
Yeah, for this one, for the final strong classifier, the threshold is 0.5, or you pick the best threshold to get the last decision boundary.
Oh, you just do the sign. So you do this weighted linear combination of these classifiers.
Okay.
And take their sign.
So the individual classifiers are +1 or -1. And so the usual sign for that would be 0, not 0.5.
Okay.
Right?
Yeah.
Like the usual threshold would be 0, not 0.5.
Yeah, right.
You
so yeah,
could
it's
adjust that threshold, but people don't
yeah, oh,
really bother.
Right.
Okay. Do you have a theory that states whether so if you get the strong classifier, enough number of the weak classifiers, you get an arbitrarily complex or expected?
Yes, and again, we may or may not have time. If depending on interest, we can do that in more detail. But there is theory that supports this. At least there is theory which says, well, what happens as I let the number of iterations go to infinity? Yeah. You can argue that you are going to drive your training error down to 0. Okay. And there is also results on how close is the training and the test error based off of how many iterations you have let it run, and what's the properties of your weak classifiers, like how complex they are. Actually, yeah, maybe I'll talk a little bit about that to give you a glimpse. Maybe we can go a little bit into next class because you're postponing neural network. So we might do a little bit of it next time if people are interested. I think I already have the slides. So in fact, yeah, I think that's what we'll get into next. So if you want to think about why this is a good choice for the weights, why should it be based off of this weighted training error? I think intuitively it's sort of, I already made the case, it makes sense, right? We have to analyze the training error. At least one reason we actually might want to do that is to understand that even though this is a rule that was just proposed, makes intuitive sense, there is actually a specific objective function that boosting is optimizing. So just like SVM, I mean, of course, the final goal we have in mind is to minimize the probability of error, right? Just 0-1 loss. But like SVMs did not directly target 0-1 loss. What was the loss SVMs were targeting? There was a name for it we discussed? Hinge loss, right? Yeah. So SVMs were targeting hinge loss. You can think about other losses. We have, of course, talked about the squared loss for regression. If you think about logistic regression, it's also, even though we just assume a model, it's also targeting a loss. I could give it away, or you can think about it. Maybe we'll talk about it next time. What's the loss logistic regression might be optimizing? It's just doing maximum likelihood, right? But you can think of that as also a loss function. Maximizing the likelihood is equivalent to minimizing something, right? So anyway, so you can think of a different loss, and you'll see that all of these loss functions are actually upper bounds on the 0-1 loss that we actually care about. And what boosting is doing is it's going after yet another type of loss, which is called the exponential loss. And if we minimize the exponential loss, or look at it over the training data, so the training error in terms of the exponential loss, then this value for alpha t will actually pop out. This is the setting for which you get the minimum exponential loss on the training set. So depending on if people have interest, we could either do it in the next class, or it is there in the slides online, and you can go through those. But I wanted to mention one result, that we can actually do that analysis. And what pops out of that analysis, looking at saying that, oh, you have 0-1 loss that you want to control, you can upper bound it by the exponential loss, which is a convex loss, so it's easier to optimize. 0-1 is not convex. And if you optimize this exponential loss, out pops out a result like this, but also you actually can show that your 0-1 training error in terms of this exponential loss can be bounded as follows. And this thing says something interesting. What it says is, so just looking at this expression, it says that as long as epsilon t is not half. If it's half, of course, it's saying that each weak learner is completely random, right? It's not doing anything meaningful for you. So in that case, of course, you can't do anything. But as long as each weak learner is slightly better than random guessing, means epsilon t is doing slightly better than random guessing, it's slightly different than half, then the training error of AdaBoost, this is the training error, we can show a bound like this, that it's actually going to 0 exponentially fast in the number of iterations t. Right? So it says if you train for long enough, you can drive your training error down to 0. Right? Yes. So this is still about training error, not test error. And as I said, there are bounds on how far the test error can be from training error. And actually, for the boosting case, they have a nice story that people initially did one type of analysis to bound test and training error, which turned out not to explain what people were seeing in practice. Because in practice, we often see if the training error goes down, the test error also goes down for boosting. So people thought it's robust to overfitting. But turns out that was just happening. We can maybe talk about it a little bit, but that was happening because of certain margin issues in the data. It's less sensitive, or it is somewhat robust to overfitting, but it can overfit if you do many iterations. Yeah. You had a question, or that got answered? Okay. All right, so I think we're out of time, and we won't do the analysis. Again, we can either do a poll, or you can tell me right now, do you want to see the analysis for the training error for boosting, or you would like to read it up on your own? Anybody who wants to see the analysis?
Yes.
Okay, and people who don't want to see it? Oh, so that's almost equally split. I'll do a poll, yeah, and you can see if you want to pursue this further or not. But you can always look